Okay, so welcome to week 7 lecture, and welcome back once again from the holiday. What we are going to cover today is going to be two topics. The first one is going to be the grinding and the other abrasive processes, and the second one is going to be the non-traditional machining processes. So in the grinding and other abrasive processes, we are going to talk about the grinding and related abrasive processes. In the non-traditional machining, we are going to cover the mechanical energy processes, the electrochemical machining processes, the thermal energy processes, chemical machining, and the application consideration in these applications. So first we are going to talk about the abrasive machining. Now you remember what we have done at the first part of the semester. We talked about how to shape the material. So we talked about the casting process. We melt the material, we reshape it in a mold. And we said that sometimes this process can be a net shape process or near net shape process. That means we are going to require to do a little bit machining on it to have the accurate shape. The disadvantage for this process was too much energy to melt the material and shape it once again. And also we are going to have non-accuracy with the size due to the expansion and contraction of the material. So we had the deformation of the material. We said we can take the material, we can forge it, we can roll it, we can punch it, okay, to make a new shape. And once again we said this was not enough to finalize the product. So we talked once again about the cutting machining, how to use the drilling, the milling, the turning to cut off part of the material in chip form to reshape the material into a new shape which is going to be similar to the designed part. And this will have very high accuracy due to the cutting process. So we said we had to remove the material as a chip form. That means we have to go for the depth of something between 0.1 millimeter up to, let's say, 4 millimeter in most of the cases. The main problem we are going to have in the cutting process is the surface finishing. Whatever you try to do, the surface finishing is going to be sort of rough, and you check that when we had the metrology lab. You saw the samples. If you remember that we had the samples from the left to the right, some of them were quite fine and the other side was coarse. The coarse was simply done by the machining. The one on this side was done by something we called super finishing. How we can do the super finishing, or the finishing of the surface to have it bright and very fine? We do a process called the grinding process. The abrasive machining is type of the grinding process. Is to remove the material now as a very fine layer, and the form of the material to be removed is not going to be as a chip. It's going to be somehow as a powder. Okay, so we remove material as a powder, a very fine layer, to have a very good surface finishing. So the abrasive machining is a material removed by the action of a hard abrasive particle, usually in the form of the bonded wheel. That's the usual thing. But have you ever heard about something called the sandpaper? It's abrasive process. Now once again, because we are going to have a hard abrasive particles, well, it's going to be on a paper. You remember that, well, I'm going to go from this one to be an introduction for the grinding process, the abrasive process. You remember that we have two types, and multiple types, sorry, of sandpaper. We have the coarse one and we have the fine one. The coarse one is going to give you less surface finishing, and the better surface finishing is going to be with the fine one. Now, for the coarse and the fine, which one is going to contain more particles? Which one is going to contain more particles? The fine one or the coarse one? The fine one, because small at the same area, so it's going to have more density, and that's what we're going to talk about when we are going to describe the grinding wheel. So generally they use as a finishing operation after the part geometry has been established by the conventional machining, which is the cutting machining. So we remove a high material, as you remember, for the rough cutting, And for the finish cutting, we reduce the depth of the cut. And to make it less depth, for having better finishing, we do the grinding to remove it as a powder. So the grinding is the most important abrasive process, and other abrasive processes can be the honing, the lapping, the super finishing, the polishing, and the puffing. The advantages are we can be used on all types of the materials. You can use it on the wood, on the plastic, on the metal. Some can produce extremely fine surface finishing up to 0.025 micromillimeters, and this is on the well, you remember the sample you used for the surface finishing machine. What was the surface finishing we had there? 2.97 micromillimeter, right? But the other specimen was 0.6, and we can go further to 0.025 micrometers. Some can hold dimensions to an extremely close tolerances, because the removal of the material is very fine. That means we can go in 0.025 millimeter depth for each cut. So this is a grinding process for a shaft, for example. You can see that we have the wheel, and the part itself is turning. When we are going to have the contact, you will start to remove the material. You can see that the friction will generate these sparks. So the grinding is a material removal process which the abrasive particle arc contained in the bonding grinding wheel that operate as a very high surface speeds. The grinding wheel usually is going to be a disc shape, wide disc shape, because it's rotating very high velocity. It should be symmetrical shape, circle one, so we're not going to have any inertia to push it to the side. We're going to have balancing for this shape. So as a disc shape, and precious have to be balanced for very high rotational speeds. The grinding wheel consists of an abrasive particles and bonding material, something like the sandpaper itself, but instead of bonding the material on the paper, we can bond it on the shape of the wheel. The abrasive particle accomplish the cutting, and the bonding material holds the particles in place and establish the shape and the structure of the wheel. The parameters we should have of the grinding wheel is the abrasive material, the grain size. It's either going to be rough or it's going to be fine. The bonding material itself, the wheel grade, and the wheel structure. The properties of the abrasive materials are it should have high hardness, because it's going to cut metal, for example. The wear resistance, we want it to last longer. Toughness, we don't want it to break up due to the impact with the material. And the favorability for the capacity of the fracture when the cutting edge is going to be dull, so the new sharp edge is going to be exposed. I'm not going to use the same surface all the time. For example, the diameter of the disc I'm going to start to use is going to be something about, let's say, 200 millimeters. Just keep using it until it's going to be 100 millimeter. So if the material is not going to be friability, then it's going to continue just using its properties and not going to do any cutting. It's going to be very fine surface touching the hard material without doing any cutting process. The hardness of the abrasive materials, according to the material we can use in the abrasive materials, are the aluminum oxide, which have the new hardness of 2100. The silicon carbide 2500, and the maximum one is going to be the diamond, which is 7000. But once again, as we said, for the cutting tool itself, this will be the most expensive one. By the way, this one, each material and on what we are going to use it. The grain size, the small grit is going to be producing better finishing. And that's something, as we said once again, for the sandpaper. If I get to have larger grit, the sizes permit for a larger material removal rate. So that means if I want to take it to closer to the dimension, I have to start with a larger grit, remove the material at higher rate, then do the super finishing by using the small grits. The harder work for the material requires smaller grain sizes to cut effectively. For the softer material require larger grid size to remove the material at higher rate. The grid size is measured using the screen mesh. And the smaller grid size is indicated by the larger number in the screen mesh produced, and the vice versa. That means the larger grid is going to have a less number. Now what we're talking about is the density. How many particles we are going to have in a specified surface area. Now that's how the screen mesh is working. If you are going to have a small screen mesh, small squares, that means that the particle is going to be finer, and vice versa. The grain sizes in the grinding wheels typically range between 8 for the coarse, very coarse grinding wheel, and for the 250 for very fine. Now once again, this is the density. Higher density, that means we are going to have finer grinding wheel. The bonding material properties. First, it must withstand the centrifugal forces and very high temperatures. Because we are going to have contact, we are going to have very high temperature. Must resist the shattering during the shock loading of the wheel. So if you are going to have a direct contact between very high impact between the wheel and the part, it should resist the fracture, because that's for the safety of the people who are standing around. Must hold the abrasive grain rigidly in the place for the cutting, yet allow the one of the grains to be dislodged and expose a new sharp grains. The wheel structure, we are going to have a simple calculation for that, but actually you have to check what we have on the UTS online for the calculation. Now once again, I have to remind you that we passed half of the semester. Now we still have another 6 weeks to the final exam. That's means if you are going to work on a double effort, you will catch up if you hadn't started yet. Anyone here started to prepare for the final exam? Oh, good. Yeah, I know, you put it in your head that way. Okay, now anyway, well, you still can catch up. You can get the copy of the book from the internet if you don't want to buy it, and you can practice on the end of the chapter questions. Now, I think as you know the topic, you can locate where you can find what chapter we're talking about. You will find the list of the end of the chapter question. Try to practice on that. Check your answer against the book. If you found that you're right, that's when you know what you're talking about. If you found some points are wrong, try to understand what's happened, and you will memorize that at the moment you are going to start reading it. So the wheel structure refers to the relative spacing abrasive grain in the wheel. And in addition to the abrasive grains and the bone material, the grinding wheel contains air gaps or pores. Because it's particles, it's grains. Whatever you try to compact it, you are going to have cavities in between. So the volumetric proportion of the grain, bond material, and the pores can be expressed as that the total volume, which is 1, which means i.e. 100% of the volume, is going to be the adding of the gaps, the bonding material, and the particles. If you add them all together, it's going to consist the volume of the disc. Okay, so this is typical structure of the grinding wheel. As we said here, we have the bonding material, the gray, the particles, and the porous air gaps in the middle. That's the volume, 100% or 1. So the fraction of each part is going to consist the final volume. So it refers to the relative spacing of the abrasive grains in the wheel, measured on the scale from open to dense. Open, that means we're going to have bigger gaps. Dense, that means it's going to be close to each other. The open structure PB means the relatively large, and PG is the relatively small, when the clearance for the chip must be provided. The dense structure means PB is relatively small, and the PG is larger for the better surface finishing and dimensional control. Now, obviously, we are talking here about the open structure, which is going to have coarse material, and this one is going to be for the fine material. The wheel grade indicates the both strength and retaining the abrasive grains during the cutting. and that depends on the amount of the bonding material in the wheel structure or the PB. Measured on the scale from the soft to hard. Soft wheel lose the grain readily. Now I highlighted this one. I don't remember why I highlighted, but I think that was a question somewhere. So now you will know what do we mean by the soft wheel and the hard wheel. So the soft wheel is going to lose the grain readily. As you do the cutting, you can see that the material is going to be not only the powder of the material you're cutting, you do the grinding for, but also the powder coming from the wheel itself. So it's used for low material removal rate and hard work material. For the hard wheels retain grain, used for high stock removal rates and soft work materials. So as you can see for the grain here, what will be the type of the wheel we are going to use. For the low, for the workpiece is going to be hard or fragile. So you go for the soft cutting tool, soft abrasive wheel. For the contacting area, wide. For rotational speed of the grinding wheel, low, high. And for rotation of the speed for the workpiece, under the low is going to be low. On the other side, for the workpiece is going to be soft and tough at the same time. We are going to go for the high or the hard disc, and the other things will follow. The shape of the grinding wheel is not the same in all the cases. We can have the straight one, which is the easiest one to manufacture. It's just compacting the things together, and we're going to have a wheel. This is the cross-sectional of the wheel. And we have the recessed two sides. So it's going to be, we're going to have recess in the middle. And we can have the metal frame wheel. So actually it's going to be a metal wheel. Then we can dress it from the outside with the material by using the bonding, as you can see here on the side. And we have the abrasive cut-off wheel. Have you seen this one? The one they're using with the manual grinding process. It can do finishing as well from the side, but usually it's used to do the cutting process. Simply, it's going to be thin, so it's going to do the cutting process. The surface finishing. Not all the part is going to be cylindrical, which can rotate on the machine. We have something called the grinding machine. We have the table, which is going to move, oscillating forward and backward, and the wheel will do the work on it. Usually, we're going to have cutting fluid to reduce the friction between the parts. So, for the surface finishing process, most of the grinding operations are performed to achieve a good surface finishing. That's the basic thing. The cutting is an extra process, not the main process for the abrasive. The best surface finishing is achieved by the small grain size, as we said earlier. You can see how shiny this surface is. Higher wheel speed, denser wheel structure, which obviously is going to be small grain size, and that means we are going to have more grades per the wheel area. So once again, remember, if we would like to have better surface finishing, we have to go for the small grain size for the wheel, higher wheel speed, and denser wheel structure to do the process of the surface finishing. We have three types of the grain action. So what the grain actually doing? They're doing the cutting, as you can see here, just removing the chip. It's very small chip, so it looks like a powder. Do the plowing process, and we do the rubbing process. That's depends on the depth of the gut you are going to insert the wheel inside the material. So the cutting is the grid projects for the enough into the surface to form a chip. The material is going to be removed. If I'm going to do the plowing process, I'm going to take it a little bit out. So the grid project into the work, but not far enough to cut. The surface is deformed and the energy is going to be consumed. But actually no material is going to be removed. The rubbing, well, from the name, a grid contact surface by only rubbing the friction occurs, which consume energy, but no material is going to be removed. We're only going to rub it to reshape it once again. So these are the three types of the grain action we can have for the grinding wheel. Because we are going to have contact, between the grinding wheel and the material, definitely we are going to have friction, and this friction will generate temperature. So a heat generated in the grinding due to the high friction, and the high workpiece surface temperature can cause damaging effects and include the surface is going to be burned or cracks. Very high temperature, concentrated in a small area, that's what will happen. Meteorological damages immediately beneath the surface, because if you are going to change the temperature, definitely you are going to change the property, meteorological property of the material. And softening of the work surface if the heat is going to be treated, and the residual stresses in the work surface as well. So actually you are going to complicate your process if you are going to keep it running for a long time without using the cooling fluid. You will damage your work part, so you have to avoid that. So how we can avoid that? To reduce the grinding temperatures, decrease the infeed. Don't take it too deep. That means we have to avoid the cutting process. Reduce the wheel speed. Reduce the number of the active grids per the square inch of the grinding wheel, and increase the work speed, and use the grinding fluid. Okay, now there's different, but you can see that we have two speeds here, the wheel speed and the work speed. Now in the grinding process, if you are going to do it for a cylindrical shape, the cylindrical shape should rotate. That's the workpiece rotation. The wheel should rotate on the opposite direction, then they are going to have opposite contact while the rotation. So to reduce the temperature and increase the speed of the rotating part, but reduce the speed of the rotating wheel. If we are going to do it for the flat surface, we are going to have oscillating table going forward and backward, and this will be the linear speed of the work part, and the wheel just keep rotating. Now once again, increase the oscillating speed, reduce the rotation speed for the wheel. The causes of the wheel wear, because there's no wheel will last forever. The grain fracture, when the portion of the grain is going to break off, but the rest of the grain remains bonded in the wheel. And the edge of the fracture area become new cutting edges in this case. Tendency for the grain to fracture is going to call the friability, as we said earlier. We have the arterious wear, with drilling of the individual grains, resulting in flat spots and rounded edges. Analogous to tool wear in the conventional cutting tool, and caused by similar mechanisms as in conventional tool wear, including diffraction, diffusion, and the chemical reactions. And the last cause of the wheel wear is the bond fracture. The individual grains are going to be pulled out of the bonding material. Depends on the wheel grade among the other factors. Usually occurs because the grain has become dull and due to the attrition wear, and resulting the cutting force become excessive. So you can see that the typical wear curve in the grinding will look similar to what? Have you seen something similar to this graph before? The volume of the work material removed and the volume of the wheel wear. Now, away from that, we have something about the tool life and the velocity we had. It's something similar to that. So, as long as you are going to remove more material, you can see that the volume of the wheel wear will simply going to increase. If I'm going to take it deeper inside the material to remove more material rate, I'm going to reduce the increase the wear of the wheel at the same time. So the wheel wear is plotted as a function of the volume material removed rather than as a function of time, as we did with the cutting tool. The slope of the wheel curve is going to be given as GR is equal to the VW divided by the VG. GR is the grinding ratio we are going to have. VW is the volume of the work material removed, and the VG is corresponding volume of the grinding wheel worn. When we are going to have the wear for the wheel, we have to make it come back to life once again. We said that the wearing, that means it's going to have very fine surface. and not going to do the action of the abrasive cutting. So the solution to make it work again is to make it rough once again. How we can do that? We do the process of the dressing of the wheel. It's how to make the very fine surface rough once again to do the cutting. So we can do the abrasive stick, this one. The wheel is going to rotate, fix this one in a certain place, and it's going to generate rough surface once again. Rough and a flat surface. Because the wheel usually is going to be a concave shape, especially if I'm going to use it to sharpening cutting tools. Use the rotating disc, and both are rotating disc and both are abrasive sticks. So the process of the dressing of the wheel is the reshaping of the wheel. Now you have to remember that. Now even when the lady's wearing a dress, they're reshaping themselves. When you put anything on the salad, you're reshaping the salad taste. So the same thing when you do the dressing. I want you to remember that because it's highlighted. So it's accomplished by the rotating disc, abrasive stick, or another grinding wheel held against the wheel being dressed as it's going to rotate. So it's either going to be done by the rotating disc, as abrasive stick, rotating disc, or having another abrasive wheel rotating on the opposite direction. The function of the dressing are break off of the dull grids to expose a new sharp grains and remove the chip clogged in the wheel. And it's required when the wheel is going to be a third region of the wheel curve. We saw that we have 3 regions. So the third region, that means it's going to have very fine surface and are going to do the grinding operation. So you have to dress it to have a fresh new surface to do the cut once again. Done with that? Okay, so the surface grinding have 4 types. Horizontal with reciprocating work table, when the table is going to be oscillating forward and backward, and the wheel is going to rotate in position. We can have it as a horizontal spindle with rotating work table. So the work bar is going to rotate, and the wheel is going to be rotated around itself. And we can have it with the vertical spindle with the reciprocating work table. Okay, now it's opposite to this one. The horizontal, the vertical axis is going to be the axis of the rotation, or the vertical spindle with rotating work table. So we just change the direction of the rotation to have the work. Is that the only types of the grinding we have? These are the 4 types for the surface grinding for the flat surfaces. We still have other operation if we would like to do the cylindrical grinding process. So the surface grinding, once again, is we are going to do it on the flat surfaces. Well, you used to have this machine in building 2, and the student was able to see what's going on. I'll try to play a video for that to show you how the process happened. So the surface grinder with the horizontal spindle and the reciprocating table, which is the most common grinder type. And we have the cylindrical grinder, where we are going to have 2 types of the cylindrical grinding, either the external one or the internal one. You're supposed to start with the major project of the gear pump this week. Now, you will go with the sessions one by one. At the end of the session, just remind me to send you the video. We'll show you the whole process from A to Z. The whole 4 weeks is going to be simply compressed in 1 hour video, and this will help you a lot to write down your report. But remember something, rule number 1 we are going to have in this project is that the shaft of the gear is not going to be casted. It's not casted, okay? Why? It should be hard enough to take the load, the torsion load, and the other things. So we are going to have a bar, and we have to cut this bar to a different dimensions and do the cutting of the gear as we saw on the milling machine, for example, as we saw in the cutting of the gear processes. The other thing we have to remember is that we are going to have surface finishing by using the cylindrical grinding for the side, which are going to be rotating side with the pushes. We have to hold the top of the shaft to do the work. And once again, away from the lecture, how we can simply find the volume of the part you have. Well, you'll be asked to find the volume of the shaft gear. How we can find this volume?
You need to know how many material you're going to do.
Yeah, yeah. You have to know what the percentage of the material you'll remove, right? So how can you find that? Well, one of the suggested thing in the sheet you are going to have is tell you, okay, now we try to put it in the water, and you will find what the volume of the water will be raised, and this volume will be the volume of the shaft you had. Actually, I can give you a simple way. Now you know what the material of this of this shaft, then you can find its density. Okay. I think it's something like 7,300 kilogram per cubic meter or 7,800 kilogram per cubic meter. Now, if I know its density, I can put it on the scale, and I will find that its mass is going to be 1557 grams. I remember that. The shaft mass is 1557 grams. Then you will consider what was the original cylinder volume, and that's very simple. Because what's the maximum diameter you are going to have for the shaft is the diameter of the gear. You add 2 millimeter from each side, and the height plus 2 millimeter from each side, and you will have a cylindrical shape with known diameter for the base and known height. You will find the volume. Now we have two volumes, subtract, and you will find the volume of the removed material. So now back once again to the lecture. We talked about the surface grinder is going to be a flat surface, and we have cylindrical grinding if I'm going to have cylindrical surface, and this is divided into two types, either external or the internal one. So also we again have the external centerless grinding. That means that the part is not going to be supported with from the ends. Simply we are going to leave it between the grinding wheel, and we have the regulating wheel which is going to hold it from the other side, push it toward the grinding wheel. Okay, this one is called the external centerless grinding process for these cylindrical shapes. We have something called the creep feed grinding, where the depth of the cut of 1,000 to 10,000 times greater than the conventional surface grinding, and the feed rate is going to be reduced by the same proportion. Now you can see that what is the depth of cut we are going to have in the creep feed grinding. Actually, we're doing removal of the material by using the grinding wheel. So the material removal rate and the productivity are going to be an increase in the creep feed grinding because the wheel is going to be continuously cutting the material. In conventional surface grinding, the wheel is engaged in cutting for only a portion of the stroke length. Okay, so this is a conventional grinding. We said that the material to be removed is going to be very thin. We have to remove it by layers for multiple times. If I'm going to remove it in one shot, that's what we call a creep feed grinding process. We're going to insert it by 1,000 to 10,000 times greater than the process of the conventional grinding. Other abrasive processing are the honing process, for example. You see that the grinding wheel now has become different, but the process remains the same. Grinding wheel, contact with the surface, and start to remove the material and make it better. Now, obviously you can see that one of the operations we have for the honing, changing the surface range for the internal cylinder. Well, I should tell you that earlier in the previous project, but I didn't want to jump the steps. So the abrasive process performed by a set of the bonded abrasive sticks. These are the sticks bonded to the wheel, which is going to rotate, using a combination of rotational and the oscillating motion. So it's not going only to rotate, but it's going to go forward and backward. The common application to finish the bores of the internal combustion engines, and the grid size range is something between 30 to 600. So once again, it can be coarse and it can be fine, but it's not very fine. The finest thing we can have something around 800. The surface finishing is something between 0.1 2 micrometers up to or even better. It's going to create a characteristic cross-hatch surface that retain the lubrication as well. So you can see that on the side, it's not going to be simply very fine surface, because we want to keep the oil during the process of moving the cylinder for lubricating process. Also, we have something called the lapping. In the lapping, we're not going to have a direct contact between the part and the grinding wheel. Actually, there's no grinding wheel. We're going to have a material which are going to do the abrasive process. So we're going to use a fluid suspension of a very small abrasive particle between the workpiece and the lab, which is the tool. So this one is going to rotate. We're going to feed the solution in between, the suspension in between, and then the process of the lapping will occur. So the lapping compound, fluid with the abrasive general appearance of the chalky paste, and the typical grid size something between 300 to 600, and most of the application is going to be for the optical lenses, the metal bearing surfaces, and the gauges. Now, before I get to pass this one, do you understand the principle of that? Okay, so it's not direct contact. The lapping is only going to do the motion, and the solution is going to do the grinding process. We also can have the super finishing for the cylindrical shapes, which is similar to the honing, using a bonded abrasive stick pressed against the surface and the reciprocating motion at the same time. Difference with the honing are shorter strokes, higher frequencies, lower pressure between the tool and the surfaces, and we are going to use smaller grid sizes. Okay, now we finish with the abrasive cutting. The second part for today is going to be the non-traditional machining. Now, most of the machining we done earlier was removing the material by using mechanical methods. Is that the only way to remove a material? If I'm going to put any chemical on the wood, it's going to eat the wood and do the grooving process. That's cutting, right? If I'm going to have, for example, using the oxyfuel torch to remove the material, now this one is not mechanical, non-traditional methods. I can use the electrical spark, and I think you saw that before. Have you tried to, sometimes it's happened by accident, when the spark plug is going off and the cable will start to hit the metal and leaving some scratches? So actually it's removed material. How many tried that? How many of you tried that? How many of you got the shock from the spark of the car engine? It's hurting. I hate it. Anyway, but it's good for the heart. So the non-traditional process defined as the traditional machining, mostly going to be based on the removal of the material using tools that are harder than the material themselves. That's mean we're going to use the mechanical method to force this cutting tool inside the work. Non-traditional processes are a group of the processes that are going to remove the excess material by techniques involve mechanical once again, but we're going to use as well the thermal methods, the electrical or the chemical energy at the same time. Or maybe it can be a combination of all the energies together. They do not use sharp cutting tool anyway, in the conventional sense of the cutting. The advantage we can have for the non-traditional processes are can machine and newly developed metals and non-metals with special properties that make them difficult or impossible to be machined by the conventional methods. If I not simply can cut with the conventional methods, I have to use the non-traditional method to do that. Can form unusual and or complex parts geometries that cannot be readily accomplished by the conventional machining. And it can reduce the risk of the surface damages that often combines with the conventional machining. The classification of non-traditional processes are mechanical, electrical, thermal, and chemical. So for the mechanical methods, mechanical erosion of the work material by a high velocity stream of the abrasive or fluid or both. Now I highlighted the erosion because you always hear about something called the corrosion, and we have also the erosion. The difference in between is that the corrosion is chemical process. The erosion is mechanical process. An example for the mechanical non-traditional processes are the ultrasonic machining, water jet cutting, abrasive water jet cutting. Now it's abrasive, but we added water jet cutting. Abrasive jet machining, abrasive flow machining. Now, I can tell that from reading the names, you may understand what the concept of the working, but we are going to go further for each one. The electrical one, I have to stay near this one because I'm recording. The electrical one, we're going to use the electrical energy, like the spark I gave the example for. Electrical energy is going to be used in combination with the chemical reaction to remove the material, but the condition is that the material should be a conductor. Otherwise, if I'm going to send a spark against the plastic or the wood, nothing would happen. It's not going to attract the electrical thing. An example for that is the electrochemical machining process, or what known as the ECM. We have the electrochemical deburring, which is the ECD. We have the electrochemical grinding, which is the ECG. It's like the ECG for the heart, but different one. Don't mix up. We have the thermal non-traditional machining, where the thermal energy is going to be applied as a small portion of the work surface, and causing that the portion to be fused and vaporized. An example for that is electrical discharge machining, or the EDM, the electrical discharge wire cutting, the electron beam machining, the laser beam machining, the plasma arc machining, and the conventional thermal cutting processes. And the last one is the chemical process, where the material is going to be removed through the contact with the strong chemical etchants. So that's the example I gave you. Have you ever tried to use the adhesive on the foam? It will start to eat it. So this is an example for that. We can have the chemical milling process, the chemical blanking process, the chemical engraving process, and the photochemical machining process. Let's start to overview the processes one by one, and we are going to start with the mechanical energy processes. So the first type is what we call the ultrasonic machining, or the USM. Now, we can see that what we have here. This is the tool. The only thing that the tool is going to do is going to have very high oscillation frequency, going forward and backward very fast. And we're going to have a slurry solution. Slurry, that means, is going to be something like the one we use in the lapping process. A solution which contains an abrasive material is going to run between the work part, which is going to be immersed in this solution, and the oscillating part. So the only thing will happen that the oscillating part is going to push the slurry material, the granules we have there, against the work part, and this will start to engrave the surface. Okay, as simple as that. So the abrasive contained in the slurry are driven by at a very high velocity against the work part by a tool vibrating at a low amplitude and high frequency. The abrasive, the tool oscillation is going to be perpendicular to the work surface. The abrasive accomplishes the material removal. The tool is going to feed it slowly into the work, The also need is high, but when I'm going to feed against the work part, it's going to be very slow, because we know that the material removal rate is not going to be that high. The shape of the tool is always formed into a part. And for that's me, if I would like to make a rectangular shape, my cutting tool is going to be rectangular shape. Cylindrical, I have to make a circular shape, and so on. The application is the cutting of the hard brittle work materials such as the ceramic, glass, and the carbide. Also, it's going to be successful on certain types of the metal, such as the stainless steel and the titanium. The shapes include the non-round holes, the holes along the curved axis, and so on. Coining operation, which is a pattern on the tool, is going to be imprinted into a flat work surface. If I'm going to put, for example, the shape of a kangaroo at the bottom there, is going to be a high level. We're going to have the cutting of the kangaroo shape on the part I'm going to have. The chemical energy processes, set number 2 is the water jet cutting. It's very simple. I'm going to have nozzle. The nozzle is going to spray a water jet at very high speed, and this will cut the metal. Now it's very simple, like when you try to pass a punctured tube with the pressurized water. When it's going to hit your leg, you are going to feel the pain. Something similar to that, but the pressure here is going to be too high, which is enough to actually eating the material and going past to the other side. Depending on how the pressure and how close your cutting tool to your work, you can do either the cutting or you can do the graving only. So use very high pressure, high velocity stream of the water directed into at the work surface for the cutting process. The application are usually automated by a CNC or industrial robots to manipulate the nozzle along the desired trajectory. So simply the valve is going to be connected to a robot or something like the 3D printer, but in 2 dimensions and 3 dimensions for the depth of the cut, and can do the work on the surface. And used to cut narrow slits in a flat stock such as the plastic, the textile, the composites, the floor tiles, the carpet, the leather, and the cardboard. But it's not suitable for the brittle materials like the glass. The advantages is we're not going to have a crushing or burning of the work surface because you're using the water. It's not going to burn it. Minimum material loss because the jet is too narrow. That means when we are going to cut, the distance in between is not going to be more than 0.25 millimeters, something like the laser cutter. And no environmental pollution and ease of the automation. Okay, just water, you spray the water, you get water, and at the same time you just bring it back and use it once again. And the ease of the automation, because it's just simply a nozzle, you can put it on any router or any robot, and it's going to do the cut for you. For harder material, we have to mix the water with abrasive material, and in this case we are going to call the abrasive water jet cutting, or AWJC. When the WJC is going to use on the material, on the metal, abrasive particles must be added to the jet stream usually, just to make the cutting happen faster. Something similar to the mechanical ultrasound cutting. So additional process parameters are going to be the abrasive type, grit size, and the flow rate. The abrasives like the aluminum oxide, silicon dioxide, and the granites. And the grit size range is something between 60 and 120. Sorry. The grit added to the water stream is about 0.25 kilogram per minute after the stream exits the nozzle. The application usually performed manually by the operator who aim the nozzle, and normally used as a finishing process rather than the cutting process. The application is the deburring, the trimming, and the deflashing process. We can also use it for the cleaning and polishing. The work material is going to be usually a thin flat stock or hard brittle materials like the glass, silicone, the mica, and the ceramic. The abrasive flow machining, instead of using the abrasive water, we can use abrasive paste. So the abrasive particles is going to be mixed with the visualizating polymers, which are forced to flow through and around the part surfaces and edges. Polymers have consistency of putty, like that. So actually you push it from the side, you have a certain shape inside, and start to enlarge it and do the surface finishing at the same time. I think I have video on the next page. Application is deburring and the polishing of difficult to reach area of the part, like the internal cavities. You can use this one, for example, in an engine block to clean all the water passage inside. But they don't use it. Why? The machine is quite expensive. And particularly well suited for the internal passage ways that may not be accessible by the conventional methods. The other type is the electromechanical machining. Now it's mixing between the electricity and the electrochemical machining processes. So the first type is the electrochemical machining process, the ECM, where the material is going to be removed by the anodic dissolution. Using the electrode and the tool in a close proximity of the work, but it's going to be separated by rapidly flowing electrolyte. So what's happened is that we're going to take the positive going to the negative, negative going to the positive, and we're going to remove the material by passing the electrolyte all the time. So this is the electrolyte flow. It's going to be from inside the tool. The feed direction is going to be downward, and then we are going to have the material to be removed as an anode from the surface and pushed away by using the electrolyte solution. The application is the die sinking, irregular shapes and the contours for the forging dies, plastic molds and other tools. We can also use it to do the multiple hole drilling, where many holes can be drilled at the same time with the ECM, if I'm going to have multiple tools. And the holes are not going to be rounded. For example, if I would like to have a hole which have a rectangular shape or hexagonal shape, which is going to be very hard using the conventional machining. And also we can do it using for the deburring operation. The electrochemical deburring process, the ECD, which is the adoption of the ECM process as we had earlier, and to remove the burrs or the sharp corners of the part. Now once again, for this one, something like the ultrasound, the part should be immersed in the solution. Okay, and for this one is the same thing. So adoption of the ECM to remove the burrs or the sharp corners of the hole on the hole's metal parts produced by the conventional through-hole drilling process. So my aim is to cut at this area, not like the ECM to cut the whole thing. The electrochemical machining process is another one, is the electromechanical grinding process, or we know it as the ECG. Now it's similar to the grinding process. The difference is that the grinding wheel is not going to be in direct contact with the work part. Now once again, we're taking the anodes from the positive part, which is the work part, to the negative part, which is the grinding wheel. And is going to be once again going to be pushed away due to the electrolyte flow of the solution. So a special form of the ECM, which is the grinding wheel with the conductive bond material, is going to augment the anodic dissolution of the metal part surface. The application is the sharpening of the cemented carbide tools, the grinding of the surgical needles and other thin wall tubes and fragile parts. Advantages are debellating, responsible for 95% of the metal removal, and because of the machining is mostly going to be done by the electrochemical action, the grinding wheel will last much longer because it doesn't have any actual direct contact with the part. Now the third type is thermal energy processes. Usually we are going to have very high local temperature on the part, and this will cause the evaporation of the material. So the material is going to be removed by the fusion of the vaporization of the material. The visual and the meteorological damage is always going to be happen to the new surface, and that's something you're going to learn also from the process of the welding, we're going to cover later. And we're always going to have an area called the HAZ, which is the heat affected zone. It's going to be burnt, reach a high temperature, but not enough to melt the part, so it's only going to change its structure of the shape. In some cases, the resulting the finish is going to be too poor. That means we are going to have an extra process required to treat the surface. So the first type is the critical discharge processes. Once again, it's similar to the chemical one, but we're not going to attract the material and take it out. Simply, we're going to use the spark, as you can see here, and it's going to etch the surface at very high rate. Then we're going to have the material to be removed. Once again, we have to use the fluid to take out all the material which has been removed from the cavity. So material removed by a series of the discrete electrical discharges, which are the sparks, causing the localized temperature of high enough to melt or vaporize the metals. It can be used only for the electrically conducted work materials, otherwise not going to attract the spark. And we have two main processes for that, either the electrical discharge machining or the wire electrical discharge machining. So the EDM operation is one of the it's one of the most widely used non-traditional processes. The shape of the finished work surface produced by the shape of the electrical tool. Once again, if this tool is going to be cylindrical, I'm going to have cylindrical cut. If it's going to be a square shape, I'm going to have square cut, and so on. The spark occurs across a small gap between the tool and the work part, and we are going to require the dielectric fluids, which are going to create a path for each discharge as the fluid becomes ionized in the gap. The materials we can use in the EDM process should be electrically conducting. Hardness and strength of the work material are not factors in the EDM, and the material removal rate depends on the melting points of the work material. If I'm going to have low melting point, we're going to have higher rate of the material removal. The application are tooling for many mechanical processes like the mold for plastic injection molding, extrusion dies, the wire drawing dies, the forging and the heading dies, and the sheet metal stamping dies. The protection parts, delegated parts are not rigid enough to withstand the conventional cutting forces. Hole drilling where the hole axis is not at acute as angle on the surface, and the machining of the hard and the exotic metals. So if I would like to make a hole, it's not going to be vertical on the surface, inclined by a certain angle, I have to use the EDM instead of using the conventional cutting process. The wire EDM, I think they still have it. If you know the bridge between building 1 and building 6, and then you have to cross building 6, go into the street behind the ABC and the building 6. They used to have a robot having the wire EDM. It was used to cut special foam to do a special shape for the design school. So the process is very simple. Once again, we are going to have the wire which is going to rotate between two wheels. It does have the electrical energy, and we are going to have the dielectrical fluid run in between. So starting from outside, when we are going to have a direct contact between the two parts, the same process will occur. Okay, the spark will start to remove the material, and we are going to have very narrow cut. How narrow the cut is? Something like that. You cannot even see it, because just seam wire with electrical energy, and the fluid is going to remove the material which is going to be melted. So the wire EDM is a special form of the EDM that uses a small diameter wire as the electrode to cut the narrow curve in the work. The application ideal for the stamping die components. Since the curve is going to be so narrow, it's often going to be possible to fabricate the punch and the die in the single cut, as that. The other tools or the parts are going to be intricate outline shapes, such as the lathe form tools and the extrusion dies and the flat templates. And actually, this is the operation for the wire EDM on the metal. I hope it's going to be clear. Well, you can see that the wire is coming from one roller to another with the fluid in between. The feed rate is going to be slowly pass the wire along the desired path, similar to the bandsaw operation, and the CNC can use for the motion control. While the cutting, the wire is going to be continuously advanced between the supply spool and the take-up spool, the rollers we have at the top and the bottom, to maintain a constant diameter for the wire itself. The dielectric required using the nozzle directed at the tool work to interface or the submerging of the work part process. So it's either going to be feed from the top, or we can simply submerge the work part and the cutting tool inside. The other type is what we call the electron beam machining, or the EBM. Now, the same principle, using a high velocity stream of the electrons, focus on the workpiece surface to remove the metal by the melting or the vaporization of the metals. The application for that is work on any material, ideal for the micro machining processes. For example, the drilling of the small diameter holes down to 0.05 millimeters. The cutting slot is only about 0.025 millimeter wide, and the drilling holes with a very high depth to a diameter ratio. For example, we can take the diameter is going to be 1 millimeter, the depth is going to be 100 millimeters. Okay, or as we said here, 0.05 millimeter, but the depths can go 100 times deeper. So, can you imagine what will be the quality of the hole you are going to have? Well, I should show you a photo for that. Anyway, I will try to find something for you. So the only problem we have for this process is what you can see from the figure. What the main disadvantage for this process? It should be done in vacuum area. Okay. So the EB gun accelerates the continuous stream of the electrons to about 75% of the light speed, very high speed. The beam is going to be focused through the electromagnetic lens, as you can see here. This is the electromagnetic lens to send it to the beam to the point, and reducing the diameter to small as 0.025 millimeters. On the impinging work surface, the kinetic energy of the electron is going to be converted to a thermal energy of extremely high density, which melt or vaporize the material to a very localized area. Now, the other one is what you can see on the laser cutter. The laser cutter we have at the UTS is only able to cut the plastic. But actually, there's a laser cutter which can cut the metals. Laser beam machining, which use a light energy, again to generate light, focus it using the lens to generate very high speed beam to do the heating effect. So using light energy from the laser to remove the material by the vaporization and the appellations. The application are for the drilling, slitting, slotting, scribing, and marking operations. Drilling small diameters holes down to 0.025 millimeters, generally used on thin stock. You have a limited thin for the material. Harder material, you have to go for thinner thickness. Work materials, metals with high hardness and strength, soft metals, ceramic, glasses, and the glass epoxy, plastics, rubber, cloth, and wood. Now, you studied the light before. Can you tell me what the restriction we can have with the laser cutting? Remember, it's light. Yes, I know you know it, but you don't remember what's happened. So, if I'm going to spot a light, if I'm going to spot it on this surface, you can see the red spot, right? If I'm going to put it on a screen, computer screen, I'm not going to see the light. So what's happened? Why you can see the light here? Because it's reflected, right? But if I did it on the screen, it's absorbed. So that's what's happening. If I'm going to take the laser to a reflected surface on a laser cutter, it's not going to cut it. So you have to avoid that. So it cannot cut the aluminium, for example, because it's reflected. It's going to dissipate most of the light energy and diffusing the cutting operation. So once again, to define the laser is the light amplification by the stimulated emission of the radiation, and the laser converts the electrical energy into a highly coherent light beam with the following properties. First, monochromic, which is a single wavelength, and highly collimated, which is the light rays are going to be almost perfectly parallel to each other. These properties allow the laser light to be focused and using the optical lenses into a very small spot with the resulting of the high power densities in this spot. And that's how the laser cutting on the metal work. Just like a knife on a butter. So, if the surface is reflected, I still need to cut it. So I have to think about something else. I can use the plasma arc cutting. Instead of using the light, I'm going to use the plasma stream to do the process. So no light is going to be reflected. So the plasma is using a plasma stream operating at very high temperature to cut the metal by the melting process again. The application, most of the application of the pack is involve the cutting of flat metal sheets and plates. The whole pressing and the cutting along the defined path can be operated by handheld torch or by automated by the CNC. Can cut any electrically conductive material, and most frequently cut metals are going to be the carbon steel, the stainless steel, and the aluminium. So if you can read here that the plasma is superheated electrically joined ionized gas. The temperature is something between 10,000 degree up to 14,000 degree, and the plasma is going to flow through water-cooled nozzles that's going to be construct and direct the stream into the desired location, and the plasma arc is generated between the electrode and the torch and the anode on the workpiece. So this will be the negative part, and this will be the positive part. That's when we'll make the flow of the plasma going in this way. Now, once again, it's not perfect operation. The temperature is too high, which can cut highly reflective surfaces. But the problem is, it can damage the surface. That's why they're cut under the water, just to reduce the heat affected zone. Number two, laser cutter can cut the plastic, for example. This one will damage the part, just melt it. The air carbon arc cutting, I think you saw this one before. So the arc is generated between the carbon electrolyte and the metallic work. So that's what will happen. We're only going to have the arc is going to generate between the two parts. And at high velocity, air jet blows away the molten portion of the metals and can be used to form a curve to surface of the piece, or gauge the cavity to prepare edge of the plates for the welding process. The separating of the molten metals is a hazard and disadvantage in this process, and the work materials usually is going to be metal with a steel thing, like the cast iron, the carbon steel, alloy steels, and various non-ferrous alloys are possible to be worked with. Other arc cutting processes are which are usually not widely used as the plasma arc cutting and the air carbon arc cutting, are the gas metal arc cutting, the shielded metal arc cutting, the gas tungsten arc cutting, and the carbon arc cutting. The oxy-fuel cutting, the same device we're using for the welding, we can use it for the cutting. Now we're generating very high temperature due to the burning of the oxy-fuel gases. So once again, the oxy-fuel cutting process using the heat of the combustion of the fuel gases combined with the exothermic reaction of the metal with the oxygen. I think we have something here. Probably known as the flame cutting. And the cutting torch delivers a mixture of the fuel gas and the oxygen and directed as a stream of the oxygen to cutting region. The fuels we can have are the acetylene, which have the highest flame temperature and most widely used, but usually is dangerous. It's hazard to be used. We have the MAP, we have the polypropylene, the propylene, and we have the propane. The application usually is going to be performed manually, but we can also put it on the CNC to do more neat shapes. Manual operation examples are for the repair work, cutting the scrap metal, the trimming razor from the sand casting. The machine flame cutting allows for faster speeds and greater accuracies, and the machine operation is always going to be a CNC control to cut the profile shapes. I used to have a good video for that. I don't know where is it. Anyway, the other types in the now we are going to cover the fourth type, which is the chemical machining. Now, if I would like to make any cut using a material which is going to have a corrosion inside the surface, the first step I have to do for nice cutting is to have the cleaning for the surface. So the first step in the chemical machining is cleaning to ensure that we are going to have uniform etching. We have to do the masking process. The masking, which is going to be chemically resistant to the etchant, is going to be applied to a portion of the work surface which is not going to be etched, and then we are going to have the etching process, which the part is going to be exposed to an etchant that chemically attacks those portions of the work surface which are not masked, and we are going to have the demasking process, which is the masking is going to be removed. Now, if I'm going to explain this one to you once again, have you ever tried to, well, it's not the graffiti, but something like, have you tried to use the spray paint to put something on the wall, and you use the paper card to cut the things inside? So the paper card is the mask. You clean the surface, you put the mask, you spray it, dry it, you take it out, and you are going to have the thing inside. So same process, but instead of the paint, we are going to use the etchant material, and instead of the masking using the paper, we are going to use something which is going to be resisting to this material. Spray it, it's going to start the etching, remove it, and you are going to have the cutting appeared. Okay, so the materials we can use in the masking and the chemical machinings usually is going to be neoprene, the polyvinyl chloride, the polyethylene, and other polymers. The masking accomplished by one of the three methods, either the cut and peel, where the masking is going to apply it first on the whole surface, then you are going to do the tipping, painting, or the spraying process. After the masking hardens, it's going to be usually cut by hand using the scribing knife, and it's going to be peeled away in the areas of the work surface to be attached. Used for large work part, low production quantities, and where the accuracy is not going to be a critical factor. The other types of adding the masking can be done by using the photographic resistance material, where the masking material is going to contain photosensitive chemicals. The masking is going to be applied to the work surface and exposed to a light through the negative image of the area of to be attached. And these areas are going to be often removed using the photographic development techniques, and the remaining areas are going to be vulnerable for the etching process. Application are the small parts produced in very high quantities, and the integrated circuits and the printed circuits cut. Now, to explain this process, the first one is very obvious. You clean the surface, you just spray a layer, for example, or you just put the polymer material, then you start to cut the part you would like to etch and peel this part, put the etching material, and you're going to have the shape desired. The other one is photographic resistant material. You just spray the whole surface, and you are going to expose the light, which have the negative shape. That means it's going to expose the light for the area I don't want to attach it. So it's going to, because of the sensitivity of the light, it's going to be harder material, and this will do the masking process. The rest of the area is not going to be covered. Then I can simply put in the etching material, and it's going to do the etching process. The screen resistant material, mask applied by the silk screening methods, and the masking is going to be painted through the silk or stainless steel mesh containing the stencil into the surface area that's going to be etched. Application is between the other two masking methods, or the fabrication of printed circuit boards. Okay, so this is the etching process. Okay, so we put the masking process. We expose the light, for example, it's photosensitivity. When I'm going to remove the mask, I'm going to have the etching to be painted on the work part. So the factor for the selection of the etching material is what the material you are using, what material you are going to cut, depth and the rate of the removal rate, and the surface finish requirement. The etchant must also be matched with the type of the masking to ensure that the masking material is not going to be chemically attacked and damaged. The material removal rate and the chemical machining is going to be generally indicated as a penetration rate in millimeter per minute, since the rate of the chemical attacks is directed into the surface. The penetration rate is unaffected by the surface area, because simply you put the material layer, then it's going to go down. It's not, whatever the area is going to be, the rate will remain the same. How depth you are going to go inside the material by doing the etching. Typical penetration is something between 0.02 and 0.05 millimeter per minute, and if you're going to change it to inches, it's going to be smaller. So it's quite slow, but actually we don't do very deep cutting with that. It's just do the work you would like to have. The problem we are going to have in the CHM is the undercut process. The undercut, that's my maskant, this is the edge of the maskant. The problem is because I'm using a chemical material, so it's not going to go perfectly downward. Some of the material will start to etch from the side as well, and that's what we are going to have it as the undercut process. Now, how can I simply overcome the sideway cut, or what we call the undercut process? I would like to have a cut which have, for example, this dimension, but the material will go inside. So if I would like to have the accurate cut, what am I supposed to do? So what we have done when the mold was designed and the material put inside and shrink later, so we oversize the mold. In this case, I will simply undersize the shape I would like to have on the maskant. So material will make it bigger, which is going to be my desirable size. Okay, so undersize the mask size, and this will do the work. So the chemical milling process, as you can see here, we are going to have the undercut in all the cases. So the chemical milling process, we are going to have the raw part cleaned, put the mask in, cut and peel the parts according to the dimension you would like to have. Once again, just remember that these dimensions should be undersized, because we are going to have the undercut at the end. and put it in the etchant material. Start to etching the material, and at the end, leave it to dry. Remove the mask end, and you have to have the finished part with all the details. So the application for that, remove the material from the aircraft wing and the fuselage panels for the weight reduction. The application for large parts where the substantial amounts of the material of metal are removed. Cut and peel masking methods is usually used. The chemical blanking, I think you saw these things before. It's used for the certain electrical engineering drawings. The chemical erosion to cut the very thin sheet metals parts down up to 0.025 millimeters thick and or for the indirect cutting patterns. The conventional punch and die does not work because the stamping forces damage the thin sheet metals, or the tool cost is going to be prohibitive of both. The masking methods are either photoresist or screen resist type. The photochemical machining process. Use the photoresist masking methods, applies the chemical blanking and chemical engraving when the photographic resist method is going to be used. Used extensively in the electronic industry to produce intricate circuit designs or the semiconductors wafer. Also used in the printed circuit board fabrications. The possible geometries we can have from the non-traditional processes are, if we simply summarize what we covered earlier, first we can have very small holes. We cannot have it with the conventional cutting. Holes with a large depth to diameter ratio, then once again we cannot do it with the conventional cutting. Holes that are not round, narrow slots and slabs and plates, the micro machining, the shallow pockets and surface details in the flat parts, the special countered shapes for the molds and the die applications. The work material for non-traditional machining. As a group of non-traditional machining can be applied to metals and non-metals at the same times. However, certain processes are not suited for certain work materials, as we saw earlier. Several processes can be used on the metal but not on the non-metals, like the ECM, the EDM and the wire EDM and the PAM. Next lecture we are going to talk about the powder technology, and we are going to understand how does the cutting tool like the carbide insert has been made. Okay, so any question for today's lecture? I'm sorry, it's Tuesday, 8 a.m. I know you are sleepy. I didn't shout. That's why I didn't shout. Okay, so that's it for today. And if you need anything, you can simply contact me.